And it looks like the book is opened here on the interesting example 4. I think in the spirit of example 4, let me see, what's in example 4? Let's refresh a little bit. Well, here we have the sequence, and the nth term is here. Nth term is n squared over something like 2 to the power of n. Minus 1 is irrelevant. So what they say is, where does this approach to? And what they trying to show that this approaches to 0. Let's say there's a mean convergence. It can go approach to 1 or to 5, to just about any number. So as long as it approaches someplace, the nth term sequence, then we say this convergent sequence. So what they do is they decided to use the L'Hopital's rule. So they take a limit of numerator and denominator when x approaches to infinity, and then they take derivative. So first derivative will give us 2x, and the second derivative of 2x is going to be 2. For denominator, first derivative, according to the formula, it will be 2 to the power of x times ln of base, which is 2. And then again, notice that ln of 2 is a constant. So I'm going to use the same exact formula again, so it will be multiplied by ln of 2 and 2 to the power of x, and ln of 2 is multiplied with itself twice. So the point of story is that we have 2 to the power of x left on the bottom, and 2 to the power of x approaches to infinity. And when you divide a fixed number by the big by infinity, the result is small or 0. So it's ended up being approaching to 0. And I think there should be an exercise that discusses this in general. So let me go to the section end in the exercises, where you can't really use L'Hopital's rule, because it looks like for the power of 2 we used it twice. But if I try to see like 65, exercise like 65, for example, then notice that in 65 we have power of p. So if power of p is a 2, so just to compare, we had, let's try to put an arrow. So that's power is p. So we had power of 2 of n, and we divided it by 2 to the power of n. And that was approaching to 0. I say that was minus 1, Alex. Well, minus 1 did not make any difference. If you subtract 1 or 2 or 1,000 or 1,000,000 from the term where n approaches to infinity, then it wouldn't matter that number that you add or subtract. So it's still the same 2 to the power of n. So that's what was shown already in example, was it, I don't remember, 3 or 4, I think 4. But here's analog of it. Now the power is not 2, but n. So it could be 1,000, 1,000,000. So you definitely don't want to 1,000,000 times use L'Hopital's rule, right? Because it's going to take you a long time to do this exercise. So the question will be, how can I do that? Well, looking at the analogy with the exercise when n is 2, when p is 2, so that's the case that they considered in the example. But question is, how can I figure that out? Notice that derivative of e to the power of n is still the same thing times ln of e, which is 1. So no matter how many times you're going to differentiate your denominator, it's going to be the same, right? E to the x, same thing. 28 derivative. But for a numerator, the power is going to start to decrease. So eventually, after doing this differentiation p times, you will actually end up with no power of n. So it'd be some constant on the top. I say, Alex, but that's for n to be the whole number. What n is a fractional? Well, if n is fractional, it looks like it's the same thing because power will eventually become negative, so it'll go down to denominator. And this is also going to be 0. But the reason I wanted to stress it is the approach we saw last time when enjoyed previous lecture where I shown you using the graphing calculator, and that's the reason why I do this thing. So n to the p and e to the power of n. So if I look at the graphing calculator, let's find it. Graphing calculator is in here, and if I try to graph, let me just graph the previous we did, the example that was x to the power of 2 or n to the power of 2 divided by 2 to the power of x, right? So I go 2, and the power is going to be here, x, and then we can do -1, why not? It doesn't matter, but you look at this graph, it approaches already to the 0, right? I say, okay, so what if I subtract 1? What is going to change? Well, if you subtract 1, it doesn't make any difference, right? So it's still going to approach to 0. I say, how do you see that it approaches to 0? I guess that's the very important thing to realize in here, that the graph approaches to 0, and the result is y coordinate. Y coordinate. So along the y-axis, the y coordinates of points here keep going closer and closer to the 0 because they're points along the curve that have two coordinates, x coordinate and y coordinate. And remember, we also come to realize that we don't take the whole graph, we take the sequence. So that's the first term, which is here. What does that mean? So first term is actually my A2. A1 is corresponding to x equal to 1. So that's A1. So it seemed to start to increase, but at some point, so that's my A3. So y coordinates are the terms of my sequence, A4 and then A5, and then you can start to visualize. I hope that they start to get closer to 0, right? A6, then A7. Y coordinates, that's what we care about. And then 8, 9. So this is not the curve. We're saying that for x coordinate 2, y coordinate is term of the sequence that we have here. So it should be in A2, which is right there. So for 3, it's y coordinate. So that's the way we interpret those graphs. So graphs are giving us way more than the sequence. Sequence is only a bunch of points, and not points on the curve, but points, coordinates, y coordinates that are coming on the y-axis, and they go to this place, which is happen to be 0. If they were going to 4, they would say the limit is 4. So depends on y coordinates. That's all we care about in those pictures, y coordinates. It's important to realize. So now I want to go to the actual case when p is not 2, but when we have the power, powers, just any value of p. So let me n to the power of not p, let's say if p is equal to, for example, 7. So that'd be n to the power of 7. And it is still going to be 0. And the way you can see it again, you just change your power here to 7. Okay? You say, Alex, that's not right. It is not 0. It is keep going up. Well, zoom out. You will see what happens. You see, it starts going up and then eventually it comes down. For 7, it's coming down at the level of 30. If you put 1,000, it will be coming down to some place at the probably level of, if that's 1,000, it could be 500 or who knows. But the point of story that the graph is deceiving if you don't zoom out. So you need to see the whole picture. So if I want to actually see the bump analogous to the one I saw when we had squared, then I can change my y coordinates not from 25, but say, what about if I take 250? No. Okay, another 0. 2,500. Is it going to work? I need bigger. And it's going to be negative 25. Huh. Oh, look at that. Look at what I need. So I need to go from take this away. You see, it's up to 10,000 already, where they have that local maximum and then it goes down. So we kind of need to know what the graph looks like. The point of story is you need to know what the graph looks like, because otherwise, if you just get the calculator and graph it in the standard viewing window, which is going to be like 10 by 10 or something, so you're going to see nothing. Actually, 10 by 10 is going to be a little bit more farther to the right, but it'll look like the function keeps on increasing. That's what the original window shown to me. But I had to increase my ability to see up to 10,000 all the way up, so then I be able to see that local maximum point, right? And then it starts to go down. And that's for just 7. When you say, Alex, why did you take 7? I don't know, I could have taken any number, 10, but if I took a big number like a million, it would probably take me up to billions or who knows, even trillions region. So that'd be too much. But the point of story, no matter what your power is, eventually after a bump, after the reaching point of maximum, it will start go back and it will actually give you again horizontal asymptote, which is x-axis. So for all of these functions. So the message is the L'Hopital's rule is probably not the way to go. Technically it is, but you need to, well, think a little bit more globally in terms of what if you differentiated whatever p times, because here would need probably to differentiate it 7 times to start to see that this is approaching to 0. And if you get bigger powers, then you will, I guess, have to differentiate as many times as that bigger power actually is equal to. So this is really something to think about, and it's really needs to be solved in some abstract ways. The exercise 65 in abstract ways, say you use L'Hopital's rule p times, basically. And what is p? P could be a billion, so billion times then. So this is not really something you can solve algebraically nicely on a paper. You need to discuss it. And that's the reason why I selected 65, because I think this is the only different exercise than the others are here. Here's interesting, 71, that's probably something that you already recognizing, right? It's a first special limit in the calculus. We saw number e, it's a second special limit, something similar to 70, but it's squared, but it doesn't matter. But it's the first special limit. Remember, you were using that bounded. I guess I'm going too fast to write it down. It takes a while, so let me do number 71. I think that'd be good to try. So what happens with 71 if you are dealing with sine n over n? And the fastest way we already have, take a limit, right? So see where it approaches to. And sine x over x, was it approaching to 1? You say, really, let's check this out. It's approaching to 1 when n approaches to 0. But, right? So what happens when n goes to infinity? That's different. Well, turns out that's bounded by, so bounded means you treat it as a fixed number, 1, 2, 3. So just like a fixed number over n, which is going to infinity, is a fixed number over big is small, so that has to be 0. So it approaches to 0. Bounded, BD, I mean bounded. And once again, my point was to graph. So if I go to the graphing, and I don't definitely want to use this particular window, which is very high up, so I just click back on home, so it will return back. And now I can enter sine x over x. So let me do that. So let's see, how do you enter function sine? I think you can just type it sin or use functions. So using calculator functions, and sine is right here. So you can graph any of these functions if you want. Sine of x, that's favorite. So you can see why it is bounded. It is bounded between -1 and +1, right? Again, bounded for y coordinates, because of course it's not bounded to the right and to the left in terms of x. And what we care about, what happens when x approaches to infinity? Well, y coordinates are always going to be from minus to +1, so on the y axis, y coordinates. But that's not what I need. I need to divide it by x, right? And you can see the sign starts to fade down and get closer and closer to the 0 along. So y coordinates get closer to 0 along y-axis, and actually they turn into x-axis. So if I, again, zoom out a little bit, I will see that the graph starts to have its maximum smaller and smaller. So if you just keep going and going, you will see it turns into pretty much x-axis. And that's what it means that we already noted here. The limit is 0. Y coordinates of those points are 0. So the message is, and that was key message that we saw at the end of last class, that using this beautiful graphing calculator is helping us to get the limits right away without doing any algebraical tricks, even though functions can look kind of odd, but it's all going under nice picture, y coordinates. That's what we cared about. So that's one thing we learned last time. The other parts that we might use from the theory here is that if you have a sequence which is bounded, what does that mean? Well, look at the picture. So bounded by L. So they say the analog of limit. So y coordinates, that's what we care about. So again, for a first term, for second, so whatever is in a broken line is for convenience to get a graph of function, and then we just care about the points. That's what our sequence is represented by points. And first point is here, y coordinate. Second point is here, it's y coordinate. Third point is here, y coordinate. So I don't think it's correct to put the points here along the axis. They should be here. So that's my A2, because that's what they're equal to. But they kind of trying to also justify why this is A2, because it's for the second and then for the third, but they have to be on the y-axis. That's where the actual points are. They're y coordinate. A5. So please notice they keep on going up, increasing the function, because it's horizontal asymptote. So what happens to y coordinates? Well, one can say looks like it's going upwards, right? So it's going to L from below. So the limit is L, and that's what they're discussing in here. And they do the abstract proof in terms of epsilon delta. So they say if it's keep on going up higher and higher and higher, so what if it doesn't have the limit L? Well, it's still going up, so it's not going to exceed it, so it will probably have a lower limit L. So it is interesting to read this justification, and I guess get it if you want to take. It's a really advanced calculus kind of proof. So they never give you pictures in the advanced calculus book. They just write something here. And I think they wrote even too much. They usually write less. So that'd be for you to figure out what it all means. But I guess you imagine yourself a picture and then it starts to make sense. The only problem is for advanced calculus that you cannot always imagine pictures because they might be in 4 or 5 dimensions. And that's why you just will start to do analogies. But anyways, the idea I hope is clear. So if you keep going up and up and up and bound it on the top by some kind of number, it means you must have a limit because you keep going up higher and higher. So you should get somewhere here. You cannot keep going higher because you will cross that whatever limit is probably equal to, and that's where they get a contradiction. So that's really proved by contradiction. So anyways, they took away the proof part from calculus classes. That's why I don't really try to get into epsilon delta story. But again, it's interesting. It's interesting for some people that not going to stop after calculus 2, but we'll continue with more math classes. So anyways, this is a bounded sequence that keeps going up again, is going to be convergent. But what it is convergent to, we don't show. We just say it is, in general, has some kind of limit. So it's not giving us the way to find it. It just says there exists, so-called existence type of statement, which is kind of fuzzy. So, but it's, I think, being used later. Well, anyways, so what else did we see here? If I look at the exercises, there is some interesting symbol factorial. So some examples 29 through 34 looks like deal with factorials, and they just want some students to realize how they can simplify things. So let's see if I look at 29. I'm gonna deal with 11 factorial over 8 factorial. And factorial is a sub-case of so-called gamma function, which defines not just factorial for the whole numbers, but factorial for any real number. When I say really, so for 1.5, yes, for number pi, you can also have factorial-like procedure, and it is given by so-called gamma function, but definitely when you start to see it, you say, oh, okay, Alex, enough. I don't care, because it's really getting a little bit away from the story. But anyways, factorial for the whole numbers are always products from the larger go down all the way to 1. So 8, 7. Please notice I stopped at 8 factorial because I have it in denominator, so I can just cancel these and get this 3. That's it. So that's something that is being done in all of these exercises. For example, in 32, after you cancel, you're going to end up with n plus 2 times n plus 1, because next factor will be n factorial, and it will cancel with your denominator, right? So it's pretty much everything same here. I say, what about 2 plus n? Well, that'll be 2n plus 2, and then 2n plus 1 left, and then 2n by itself will also cancel. So very similar to the upper one. So factorials also appear in some exercises. And the reason I'm trying to stress what factorial is that factorial is probably the fastest increase in function, faster than e to the x. And that's what's interesting to realize. Let me try to see if I can graph factorial. Let me use graphing calculator, because that's stuff that sometimes people overlook and don't really know. The factorial type of growth is real fast. So where's my calculator? Down here. So I think I should clean all the mess first. It's kind of too much mess. So I'm going to stop share. So I want to say a couple of words about factorial right now. So let's try to graph x. Oh, let's stop it here. So if I have x and now factorial, so I'll be able to find it among my functions. See, there are lots of functions here. Is there factorial here? Combinations, permutations, the last one's related to factorial, but let me see factorial. You don't give factorial. Okay, I can take the calculator just to show you. So scientific, just regular scientific calculator. The amazing part of the story that sometimes we see with my statistics students. So if you try, it's a shame there is no factorial function. People don't use it. It's growing too fast, I think. That's why. So for example, if you try 5 factorial, so you go to functions, and here's factorial. So it's 120. So it's 5, 4, 3, 2, 1. Okay, so what if you try not 5 factorial, but 100 factorial? Look at how big the number is. 157's power of 10, so you need to move the decimal 157 times. So what kind of number is that? Well, it's more than a Google. Google is 10 to the power of 100, right? Google, so it's spelled different. But this one is already bigger. Try 1,000 factorial. I say, what? Undefined? It's a very big number. Yes, the calculator cannot take it. That's the point. The factorial is fastest increase, because I believe you already saw that exponential increase is the fastest, faster than polynomial increase. So if you take polynomial function, say x to some power, say x to some power 5, there would be increase for polynomial functions, x to the power 5, for example. But if you try to put x in, use another color, let's say 5 to the power of x, that will go way faster. So it is coming somehow like that. But then the increase is going to be compared to polynomial so much faster that it will look like a vertical line because polynomial is not as quick increase in power as x. But if it's a factorial, it's faster. That's the point. Let's see how come it is faster. Well, let's say if you look at 5 to the power of 10, and if you look at the factorial, let's say x to the power of 10 factorial, for example. So here you have 5 multiplied 10 times with itself, right? It is for calculus, yes, it is related to graphing all the functions. And here you have, it's 10, it's not x, it's 10. So you have 10 factors in both, right? But I want you to notice that 10 factorial is already going to be probably greater because 10 is already 2 times 5. So eventually you will see that if you take 5 to the 11th power 11 factorial times 11, so instead of extra 5, then you will have extra factor 11, which is bigger. So the point of story that factorial graph, they don't even want to show you, but it is even faster. So we thought that the fastest was exponential growth, but there are faster ones, like factorial growth. That's the point. So that's something that we don't really discuss. I don't think we discuss it in regular classes. But the reason, again, I decided to show it to you is because I see the number of exercises in the textbook that deal with factorial. So where's the textbook? I need to go here. So you can see some exercises with factorial. So they're going to dominate. That's the message. So if you see the factorial here, well, here's definitely 2 over n, so it approaches to 0 because 2 are big. But when factorial is compared, like here, for example, in 54, so factorial eventually will dominate, so it'll be like fixed over 0, so it will approach to 0. So whenever you have factorials present, they always dominate. That's the idea. And of course, it's a general idea, so you need to use it to already prefix your exercise to that type of solution. I don't see many. I saw it somewhere. I think maybe they saw the example someplace in the beginning among the examples. So just to give you an idea, yeah, like here, for example. So you see that 3 to the power of n compared to n factorial. So n factorial dominates, so it's like a fixed number over big over infinity, so it is 0. So factorial is more powerful than even the power function, and that's quite amazing, right? That's new, fast, increasing kind of function. When you say, is there anything faster? Well, yes, of course. You can always come up with something faster, like x to the power of x, for example, or x to the power of x to the power of x. So there are all kinds of things that we never ever gonna even see it taken any classes because they're so fast increasing, so people don't bother with them. But the point is that you can always create something new that faster, and that's actually how the new levels of calculus are being created. So besides just regular calculus, there's regular integration, there's a Lebesgue integration, so it's like all kinds of things they were coming up, and the science is still under development. The point is they're using various things that don't have any analogs in our three-dimensional world, and that's why people say have no use. But the point is they keep on being developed anyways by those mathematicians. So anyways, next story, which is closely related, but I would say more restricted than sequence. Those are series. So I want to start to discuss series. That's what we're going to be doing in entire chapter 9. So series and sequences is what we're going to utilize to see so-called conversions or the sum of the series. So this symbol sigma stands for sum. And if you have sum from 1 to infinity, it means there's infinite sum. So your index n starts at 1, so it's A1, and then it keeps going. A2, A3, A4, and so forth. It goes up to n and continues infinitely. And the difference with this story and the previous one that we did not have summation. That we used to have just A1, comma, A2, comma, A3, but now we keep on adding those terms. So you say, wow, we're adding infinitely many numbers, so it's always going to be infinity. The point is not always, and that's the amazing. So you keep on increasing them, probably, but some of this series have finite sums, and that's what we're going to look at from now on. So series, if they have finite sum, or if they have infinite sum, so then we say the series is divergent. So word convergent means the sum is finite. So we add infinitely many terms, and it's going to be a finite sum. When you say, really, is that really possible? Yes, for example, when terms alternate in science. So the next one cancels the previous. Let me give you an example here. We should have lots of interesting examples. We find sign alternating series. See, they're all being added, those terms. And that's interesting, right? So you keep on adding them on the top of each other. So we need to, I thought I easily find it, but looks like I can't. Well, let me create one. For example, if you have -1 plus 1, -1 plus 1, -1 plus 1. You say, is that like series A n with -1 to the power of n? So if you take that sequence, and then if you, so it looks like, where does it approach? +1, -1, +1, -1. So where am I? At +1 or -1? Keep jumping between plus and -1. So it does not converge anywhere. So that series does not converge. So it's, sequence is not conversion because it's plus and -1. So not to 1, not to -1, because it keeps jumping between. What if you decide to add those terms? So if you take this terms and then decide to add them together, what would you get? Well, looks like they will plus dot, dot, dot. Cancel each other out, right? These two, one says, so if they cancel, am I going to get 0? And the answer is no. Let's see, really? Well, if you add them different way, and that's interesting to notice, if you take this alternating terms and add them like that. So leave out -1. and add these two, they will cancel these two. So it looks like everything will cancel. Now the sum is -1. So question is this going to be 0 or -1? See, I want to think about it. That'd be a good idea, but the point of story, it's not convergent. So we say it's divergent series. And it turns out because the limit of nth term is not equal to 1. It's not equal to 0. So that's the key statement for the convergence of the series. So series convergent when limit of nth term is 0. So here is definitely not 0. It's either 1 or plus or -1, and we don't know. There is no limit actually. But it could be either 1 or -1, and it's not 0, so it is not convergent. So for the example I have just shown to you with alternating terms, we don't have conversions. Let's say, so do we have conversions? Yes, of course. We'll see tons of examples from now on, and we'll definitely enjoy them. But let me go back to the beginning of this section. I know it's getting overwhelming, so maybe I'll just do one more thing and let you go and enjoy a little bit time off, because I know after the break it's hard to get back on track. So I'm not going to overload you. Just one more example, and that'd be good enough. So I will hold on to with definition, just give a couple of examples. So it turns out like part C, that's one of the classical examples when you look at the series. Sometimes it's called geometric series, because the way you can treat it as if you have your, instead of a, and I put 1/2, sum of 1/2 raised to the power of n. 1/2, that's raised to the power of n. From when n is equal to 0, we have 1/2 to the power of 0, which is 1. So when n is equal to 1, 1/2 to the power of 1, which is itself 1/2, right? Next term when n is equal to 2. So you write a few first terms, and then you will start to see right away what they described in this little formula if you go from 0 to infinity. Remember in the previous section I discussed that we have to have first term n equal to 1, but it turns out you don't have to. You can just show that your n starts at 0 or at 1, so wherever you like it. And that's interesting to realize. So that's going to be squared, which is 1/4. And then you can see that this is really example they have here in the part C. So it's described as sum of 1/2 raised to the power of n. So next will be to the power of 3, which is 1/8, then to the power of 4, 1/16, and so forth. And what's amazing thing to notice is that the sum is equal to 1. So look at this, 1/2. So that's the piece. And now I take 1/2 of 1/2, which is going to be 1/4. So if I add 1/4 to it, I get closer to 1, right? And then I take 1/2 of 1/4, which is 1/8. I get closer. So I keep getting 1/2 of distance that's left to 1. So if I keep on adding and adding and adding, then the sum is going to be 1. But of course, I disregarded this first term, so it should be plus another 1. Maybe I'll use another color so that will, I guess, give me a better visualization. So that's 1 from here, and then the rest will be also equal to 1. So if I keep adding everything else, the rest will be the red one. So the actual sum is going to be 1 and 1, which is 2. So next time I will actually discuss the formula for the so-called geometric series. That'd be very popular when you see geometric series. So your terms produced by multiplying by the same number 1/2 again and again and again. That's called geometric series. And that's convergent, means the sum is finite and the sum is 1 for the infinite part, and first term is another 1, so this is 2 in this particular case, which is quite amazing. Infinitely many numbers you add together and you get 2. And there'll be lots of examples of that, so we'll be working with them from now on. And what I'm going to do is, as promised, stop this recording for today, and we will continue dealing with this later, so on Thursday, right? So thank you.